For this video, we're going to look at Lewis structures for covalent compounds. Not hard covalent compounds. We're going to look at very simple covalent compounds. And then the next videos will build up to harder and have more of a strategy, if you will, for how to tackle them. So to begin with, let's start out with Ch4 methane, which we looked at in the previous video. So it's definitely covalent. So we can't draw it with the brackets and the charges and that kind of thing. So we need to show where the electrons are located around the atoms in a more systematic way, where we're going to be drawing lines and the dots that represent the electrons that we learned about previously. So what does this look like? Well, the number one rule is hydrogen never goes in the middle, okay? You're always going to have to make a choice as to what is the central atom in a compound. First rule, hydrogen doesn't go in the middle. Why? Hydrogen, it has one electron in its outer shell. You learned this when you drew the valence electron for hydrogen in its Lewis structure. That means it can most, if it's going to be involved in a covalent bond, which remember is sharing of electrons, it can either give up that electron like in an ionic compound, or it can share. Now remember hydrogen, it's 1s. So its orbital configuration looks like this. So in a covalent bond, another electron can be donated but shared from another atom. It can be added a dot right there, which would mean it could get another electron inside this orbital. And so it's going to share, the two atoms are going to share the space that was contained by the 1s orbital that housed the single electron for hydrogen. Similarly, we could draw the same type of thing for carbon. You had 4 electrons on our carbon. So you've got 1s had 2 in it, and then 3, 4. But these are all your p's, right? So this is 2s and 2p. And so what literally happens is when you're about ready to bond, is these atoms will spread out. Just like we might have seen some of those off-box exceptions. Erasing this orbital. So our electrons are spreading out. And now they're spread out in all of the different orbitals. And so some other element can come in and donate electrons to each and every one of these orbitals. Let me switch colors a little bit. So if I have 4 hydrogens and they all have one single hydrogen that they can donate, each of those hydrogens can come in and fill in the 4 spaces that are available for the carbon. And so those would be my 4 hydrogen electrons that are attached. Then they're basically sharing the space of the 2s and the 1s. So these will become hybridized orbitals, which we'll learn about later. Okay? Don't worry about that now. Just know that if you've got carbon and it's got its central atom here, it's got 4 electrons all around it, and you have 4 hydrogens that want to come in and share its electrons with each of those carbons electrons. What's going to happen is these guys will share with each other, these will share with each other, these will share with each other, and these will share with each other. We didn't make electrons out of thin air, we're just allowing sharing to happen in order to satisfy the octet for both hydrogen and for carbon. What do I mean by that? Carbon wants to have 8 electrons around its outer shell. Covalent bonds are a fantastic way for carbon to fulfill its valencies because it's in that middle of the periodic table. So carbon's not involved in a lot of ionic bonds. Instead, it's involved predominantly in organic covalent bonds and structures. And so in doing this, carbon, how many electrons does it now have? It's borrowing, it's sharing, if you will, these hydrogen electrons. And so it thinks that the hydrogen electrons are his as well as its own electrons. So whenever it's trying to decide if it's satisfied, it's going to count 1, 2, 3, 4, 5, 6, 7, 8. Anything it's sharing is going to count it as its own. And so it thinks it has 8 electrons around it. What about hydrogen? Is hydrogen happy? It is, because hydrogen wants to have 2 electrons in order to fill up its entire principal energy level of your 1. So because the 1, n equal 1, remember, can only hold 2 electrons in that 1s shell. And so if it's happy if it has 2 electrons in its outer shell, or 0. Is it happy? This hydrogen thinks everything it's sharing is its own. So it's got 1, 2, it's happy. Hydrogen's got 1, 2, it's happy. 1, 2, it's happy. 1, 2, it's happy. So everything is happy. And so when we draw the Lewis structure for this, our first choice is deciding what is our central atom. It goes in the middle, and then all other atoms go around it. And so our Lewis structure for this compound looks like this. Carbon, hydrogen's all around it. Instead of drawing 2 dots, we replace 2 dots with a line. So 1 dot like this is equivalent to 2 dots. Sometimes I'll see students draw it like this to remind themselves that, hey, that's actually 2 electrons. And that's fine. If that's what you want to do, go for it. Okay? So if you have something called a double bond, it's 2 lines. How many electrons is that? 1, 2, 3, 4. If you want a triple bond, how many electrons is that? 1, 2, 3, 4, 5, 6. Okay, and so these are the types of structures that we're going to use when we're drawing covalent Lewis structures. Okay, so here is the final Lewis structure for methane gas, CH4. But in order to get there, how you think about it is, how many electrons do I have around each atom, and then combine them all together. Let's do water as another example. So this is water. Let's draw the Lewis structure for each of the elements. Oxygen has 1, 2, 3, 4, 5, and 6 electrons around it. Hydrogen, each one of those has 1, and I have 2 of them. So what's going to happen is hydrogen's 1 electron is going to attach where oxygen needs it, and the other electron is going to come in and attach where it also needs the second one. And so that's why oxygen is going to have, that's why water is going to have oxygen in the middle with hydrogens on both sides. Okay? And you could, at this stage in your learning, it's okay to do this, put the electrons like this. We'll find out later that that's not really what it looks like because it's not linear. Okay? A better way of drawing water is like this. Okay, and we'll find out why later. But for right now, just draw it, okay? And what we're checking on next is checking to see if everything is happy. So we've got something not hydrogen in the middle, okay? We're going to find out later that you want the least electronegative atom to go in the middle, and you'll hear me say that a million times. But right now, not hydrogen, okay? Hydrogen don't go in the middle. Even if it's the least electronegative, which it is in this case, it does not go in the middle. Why? If you put hydrogen and then you try and bond a whole bunch off of it, how many electrons does it now have? 1, 2, 3, 4. Can it do that? No. Hydrogen can't have 2 bonds. It can only have 1. Okay? So, are all octets satisfied? What do I mean by that? Hydrogen, it's sharing all of these electrons, which means it has 1, 2 that it considers as its own. So it is happy. This hydrogen, same. 1, 2. So it is happy. What about oxygen? Oxygen considers everything it's sharing as its own. So how many does it have? 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons around it. So its octet is satisfied through covalent bonding. All right, let's do 2 more examples of covalent bonding. So the first one is chlorine gas, Cl2. So we have 2 chlorines, and they both have 7 electrons. So how are they going to become happy? Well, this chlorine is going to share their 1 electron that it doesn't have a pair with it, while this chlorine is going to share this 1 electron that doesn't have a pair. So when you then write the Lewis structure for it, that appears as a single bond in the middle with 1, 2, 3, 4, 5, 6 electrons around each of these single atoms. How do I know that? Well, just keep those electron pairs. Don't change them. You've got 3 electron pairs on each of the chlorines. Okay? When you're done, you shouldn't have just magically made up any electrons either. You should have the same number of electrons that you started with. So how many electrons did I start with? This started out with 7. This one started out with 7, which means it's a very good practice. And when our structures become more complicated, do this every time. You should start with the same number of electrons as you finish. Let's count our electrons and see if that's true. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We started with 14, we finished with 14. That is our valid Lewis structure. Okay, but how I recommend starting, draw the Lewis structure of the atoms. It'll help you think through what needs electrons and what's ready to give them up. Let's do a slightly harder one. NH4 plus ammonium. So our ammonium ion here is both covalently bound and it's a polyatomic ion. So we're going to kind of combine the two rules together, meaning the nitrogen and the hydrogen, they are covalently bound to each other. How do I know that? Let's look up the electronegativity difference. The electronegativity difference for the nitrogen with the hydrogen is 0.9, so that's very covalent. So they're not individually ions, but the whole group together is an ion. So how do I do this? Let's draw the individual atoms and their Lewis structure. So nitrogen has 5, and hydrogen has 1, and there are 4 of them. Get going. Positive. What does positive mean? It means somewhere I lost an electron. How about we just kick it off of this nitrogen here? Why? It's bigger. Why not? Doesn't matter where you took it, okay? Because the electrons are all going to flow around the whole molecule together, okay? So, but we got rid of 1 electron, so we lost an electron. So how many total electrons do I have? I have 8 valence electrons to work with. So that means on my final structure, I should have 8 or I screwed something up. So it lost 1, which means every one of those electrons is looking for another pair. Okay, it's looking for another electron to make it a pair. So this electron maybe will come in here, this one will come in here, and so on and so forth until everything has a pair. Let's see what this looks like now. We have nitrogen in the middle, connected to hydrogens, like you see here. Is everything happy? Let's check. Every hydrogen needs to have 2 electrons in order to be happy, and it does. This hydrogen is sharing 2, so it gets 2. 2, 2. What about nitrogen? Everything that it's sharing is here in the middle. So it's got 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. It's happy. But what do I do with the plus? Well, what did I do with the pluses whenever I looked at just ionic Lewis structures? You put brackets around it, and you put the charge. So the final structure here for ammonium looks like this, and you have to put the brackets with the charge on the outside or it's wrong. But the ideas are still the same, okay? You've got everything has the number of electrons where it's trying to get toward an octet. It's just if those electronegativity differences are low, it's going to be covalent. You're going to get lines. But if there is a charge anywhere on the group of atoms or the single atom, then you put the bracket and the charge on the outside.